from Bonn.
Really useful discussions and interactions with you. Things that I learned in my stay here already.
Okay. Does it work now? Yeah. Ah, great. Perfect. So yeah, just to say thank you very much for having me here. Today I will talk about consensus-based sampling. So this is something that we also discussed a little bit already in the working groups over the past weeks. And this is a collaboration with José Carrillo, Urban Weiss, and Andrew Stewart. And it's been really a great pleasure to bring together at the same table both of my mentors, José Carrillo, who was my PhD advisor, and Andrew Stewart, who was my postdoc advisor at Caltech. So this is really an outcome sort of an intersection of different topics and recent research that is very much at the heart of this program as well. Okay, so this is a brief overview of what I would talk about today. And let's start with sort of the big picture so that I can introduce to you what is this consensus-based sampling method. So we really think of this as a very generic method for sampling from some target distribution, which might be Gaussian or also more general than that. But one really sort of important application of this is in the context of solving inverse problems. And so here I'm writing a very sort of general inverse problem, y equal to g of theta plus some noise. And I'm sure a lot of you have already seen this formulation a couple of times now during the program. So the g here is a forward map, which maps some parameters theta to your observation space. Y is the data that you go out and measure, and then eta is some noise, which we here assume to be Gaussian distributed. And so there's two important questions that you might want to answer. One is, so given this model, so assuming that the observations that I have are generated in this way, what is the most likely theta? What is the most likely set of parameters given the data, right? So this would be an optimization problem, or also parameter calibration. Another question I could ask is, here's a parameter theta. What is the probability that this parameter gave rise to the data that I observe? So in other words, I would like to understand the distribution of parameters given the data. And so this would really then be uncertainty quantification. And so this is where the sampling methods come in. Now, in a lot of inverse problems that we encounter in applications, this forward map G is very complicated, or can be very non-explicit also. So we like to think of it more like a black box algorithm. So you could think of, for example, some complicated weather model where you have to solve several coupled PDEs with boundary conditions and initial conditions and so on. And your parameters theta could be something like a diffusion coefficient that you don't know, or like a boundary condition that you don't know. And there's many other sort of applications as well, of course. But in that sense, in these applications, this forward map G can be very expensive to evaluate. So you don't want to do that very often. And also because it's non-explicit in some sense, derivatives might not be available, or they might be available, but very expensive to calculate. So ideally, you would like to do parameter calibration and uncertainty quantification without having to calculate the derivative of this forward map G. And so one way of thinking about this is the Bayesian approach to inverse problems, where you assume some prior distribution of your data. And so the model that you consider gave rise to your data gives you a likelihood. And so then, thanks to Bayes' theorem, you get a posterior distribution. And now, if you assume that their prior is Gaussian and your noise is Gaussian, then that gives you a Gaussian posterior, which would look something like this, right? And so in a generic way, we can write this as e to the minus f, where in this case, f would be just a quadratic function. But you can also think of this, of course, more generally. Now, once you have this expression, you can simply forget about this inverse problem application if you like, and just say, well, we have this probability distribution e to the minus f, and I would like to either optimize, so find the maximum of this distribution, so the minimum of f, or I would like to sample from it. And so this corresponds to either the calibration question or the sampling question. Okay, so here I'm just mentioning a couple of sort of recent work where interacting particle systems turn out to be very useful to address these questions. And I don't want to go too much into detail here, but maybe just the take-home message that using interacting particle systems, for example, for evolving samples, so that you obtain samples from the target distribution that you're interested in, first of all, allow you to obtain methods that are parallelizable, since you can compute this forward map sort of for each of the particles separately, and that's usually the step that is very costly. And also, you can then look at the mean field limits of these particle systems and can do analysis on these mean field PDEs. And that usually gives you some insights and also results such as convergence and so on. So this just to say why interacting particle system is sort of a very nice tool for addressing this question. So this work, or this method for sampling, which can also be used for optimization actually, was coming out of this consensus-based optimization algorithm that was published not so long ago, so 2017. And here the idea is the following. So you set up a particle evolution where particles are driven towards a weighted mean. And this weighted mean m beta is just a reweighting with this function f that you're actually interested in. So what we want to do here is just minimize the f, right? And so by putting the information of the f into this weighted mean, you hope that you converge to an approximation of the minimum of this function. And this is due to this result here that I put at the bottom. So if you look at the mean field equation for this interacting particle system, and you look at just the normal mean of the law for these particles, over time, this will converge to some value. And that value will depend on beta, on your choice of beta. And now if you take the limit as beta goes to infinity, then this theta hat converges to the minimum of your function. And so even though in the algorithm you will just take finite beta, as long as your beta is large enough, this provides you a way of approximating the minimum of your target function without using any derivatives of f, right? That's one of the key points. And then there's another sort of important part here, which is the noise term. So you see that the magnitude of the noise is modulated depending on how far this ensemble of particles is from the weighted mean. So in other words, so this allows you to deal with functions that have a lot of local minima that are not the global minimum, and you want to be able to get out of these local minima in order to find the global minimum. So as long as the particles don't agree with each other, you keep adding noise, and the magnitude of the noise is sort of proportional to how much they disagree in some sense. And for this to work, of course, you have to start with the particles that are spread enough at the beginning. So we looked at this and thought, well, can we use this idea for sampling? And so this is basically how this project came about. Now, before I tell you a bit more about the sampling application, let me mention why this works. So behind this is the Laplace method, or Laplace's principle. And this is simply saying the following. So if I have my target function f, and now I define this r beta is just a reweighting of any measure. So I take a measure, I multiply it with e to the beta f, and then I renormalize, right? And so if I now look at integrals against test functions for this reweighting of measures, then I can look at the expansion in beta as beta goes to infinity. And the really nice fact here is that the highest order term will be a Gaussian. So this G here is a Gaussian, And it sits exactly at theta star, which is the minimum of your f, and has then 1 over beta times the inverse of the Hessian at that minimum point. So it basically provides you a Gaussian approximation of your function e to the minus f. And so this is then what's known as the Laplace approximation, which is basically just a Gaussian, right? Because this is just a constant here. So this is the key tool that we use. Okay, so I think with this, we're ready to go into what exactly is the method that we're proposing. So this is now just to introduce the notation. So the m beta and the c beta are the reweighted mean and covariance, and the m and the c is just the normal mean and covariance of any measure. And so here's sort of a very simple discrete time sampling algorithm that you could propose. And you see already that this looks somehow similar to the consensus-based optimization. The difference is that here we're adding noise with not just the difference between the particle and the weighted mean, but instead the full weighted covariance matrix. That's the first part. And the second part is that we have here a parameter gamma that we can tune. And we also put the parameter here. So now I have 3 parameters, right? I have the alpha, the beta, and the gamma. And we even started with more parameters. Like kind of the question that we wanted to answer is, if I come up with a very general family of sampling algorithms or optimization algorithms, what can I say about the parameter choices that are most useful for rates of convergence, for the behavior of the algorithm, and so on? But I won't give you all the parameter choices that we tried because these are sort of the most useful ones. And again, this is a derivative-free algorithm as it's just evolving a particle ensemble. So I will start by giving some analysis for the Gaussian case. So when this f is quadratic, just as a way of introduction and also getting some idea of how this actually works. And then I will say a few things about the non-Gaussian, more general things that we can say in the non-Gaussian case. Okay, so what we would like to do, of course, is choose our parameters in such a way that this ensemble of particles actually converges to being samples of the target e to the minus f. Okay, so this is just to repeat the algorithm. So the first thing that you can do is do explicit calculations on the moments. And so this is now in the Gaussian setting, right? So f is quadratic. And so here, the weighted mean is just a, and then the weighted covariance can be also expressed explicitly in terms of a. So that is very nice, because now if you write down the evolution of the moments for this particle model, these are closed equations, and you can actually solve them and you can study them, and this is sort of very, very nice. And so then you can ask, okay, which parameters do I want to choose now so that e minus f is actually a steady state? And this is the answer. So this is why from now on, I will always choose the gamma to be this guy. And so that also, you already see that, I was mentioning earlier that in order for the Laplace principle to work, you want the beta very large. So if I take the beta very large, then the gamma also becomes very large. And so what that means is that I'm basically rescaling the covariance as I evolve the particles. So preventing the collapse in some sense, right? Because we have seen that if we don't do that, then the particles collapse and you actually obtain an optimization method. Okay, so now this is the equation that you get on the moments. And as I said, these are closed equations. So you can just plug these formulas in and write them down. And so you get very nice rates of convergence for the moments. And so that means that if you start Gaussian, you will remain Gaussian, right? So Gaussians are propagated by this method. And the evolution then of the laws corresponding to the particles is fully characterized by the moments. And so this is basically what gives you the rate of convergence. And you see that this is exponential. Okay. And so the question is, what happens in the non-Gaussian setting? right? So for Gaussian settings, this all works very nicely. Yeah.
So alpha can be any number between -1 and 1, and beta. So
beta just has to be positive, and actually beta we would like to take very large.
Okay.
And then alpha, we were thinking of alpha as being a kind of interpolation parameter, so taking it between 0 and 1. But there's nothing that stops you from taking it between 0 and -1 as well. But if you like, just think of it being between 0 and 1. Yeah.
And if you optimize over alpha and beta, do you get something?
Very good point. So this is exactly why we wanted to kind of keep all these parameters involved, because now you can ask the question, what gives me the best rate of convergence, right? And there's two observations you can immediately make. One is that alpha equal to 0 is actually the best choice, right? Because that gives you the fastest rate of convergence. And also bigger beta gives you a faster rate of convergence without limit, actually. So the higher beta, the faster you will converge, right?
So where do you pay? You should pay somewhere. It's for free.
Well, this is for Gaussians. So I think for Gaussians, you can do many things. Where you will pay is in a way as soon as you're non-Gaussian, right? Yeah. But anyway, this serves as a good guiding principle, right? You expect that some of these things might still be true, even if you're non-Gaussian. Yeah.
So with the previous formula for M and C updates that involve a lot of matrix inverse. So when theta is large, is there any way to, unless we know they are sparse or to some extent have some structure, otherwise the inversion will be an actual cost.
Well, you don't actually solve the moment equations, right? You evolve the particles themselves. So for the particles, you don't have to do any matrix inversion.
For C, that's also the case. C, the covariance.
Well, you do have to evaluate the covariance in order to evolve the particles, but you don't have to invert it.
Okay.
But actually, in the Gaussian case, you can actually show lower bounds for the covariance and upper bounds, because you can actually write down how they evolve explicitly. And so you know what their condition number is, and so you know that things are fine. Yeah?
Beta was the parameter in front of in the algorithm. Where is beta?
So beta is just the reweighting of the means. So this is really the conceptual key point here for this method, that you want to minimize f, but instead of setting up some kind of gradient descent for f directly, instead you're putting the information of the f into a weighted moment. And then in order to get there, you increase this beta. You had another.
Cn inverse in your expression, no?
Sorry?
On the next slide. There is a Cn inverse there.
Here.
Yeah.
Yes, that's correct.
Oh, you said you don't have to invert the matrix.
Oh, I mean, if you evolve the particles, right? You don't have to explicitly compute the. Now, if you want to do analysis and you want to write down the moment equations, then yes, you do have to. Yeah. Oh, I jumped over there. Yeah. So this parameter alpha can actually be thought of as the time discretization. So this is very nice. If you think of alpha as being e to the minus some time step size. Now, if you take the time step size to 0, that would correspond to alpha going to 1. And so that actually corresponds to converging to a continuous in time evolution here. And so then what you get is this McKean SDE, which looks structurally very similar, of course, right? And you see that you have also here the 1 plus beta that blows up your convergence. Okay. Yes, and we know that if f is quadratic, so if the target is Gaussian, then e to the minus f is a steady state. And we can also show convergence for the continuum time model. But again, this is all Gaussian, right? And this is exponential in time. And here you see now that you also increase your rate of convergence as you take beta larger, but not without limits, right? This will always be less than 1. And maybe what I should say also for this rate and also for the rate in the discrete time case, these rates are sharp. So we actually have upper and lower bounds. Yep.
Short question again regarding the rates. It seems a bit unbelievable that you can really push beta all the way up to infinity. But I guess those rates are expected rates, right? So basically, these are for the expectations of the moments, right? In the mean field setting.
Sorry?
Are these rates for the mean field setting? Or?
This is for the mean field. Yes, this is all for the mean field.
Because then it makes sense, right?
It's all for the mean field.
Beta to infinity, your diffusion term becomes huge, and you immediately see the minimum of your loss, and then you can go there in one step. Basically.
Yeah. No, that's a very good point. So here, all the analysis, we did it on the mean field equations. And there's actually an important question there, sort of how to bridge now the convergence results that we know in the mean field setting to what happens on the particles. And I think that's very important actually to do. So if I write down the mean field equation for this continuum time dynamics, then I get the following PDE. And you see that in general, this is not a gradient flow necessarily, right? So here there's no gradient flow structure. Yes, and something to remark also is that even if your target is non-Gaussian, but you start with the Gaussian, then you remain Gaussian. So that also means that you can never sort of, if you start from a Gaussian manifold, you can never actually exactly approximate, like go converge to your target if your target is not Gaussian. So what you will actually get is a Gaussian approximation of your target. And that's exactly what Laplace's method is giving you, right? Yes?
Is approximation of your target distribution.
Sorry?
I mean, the mu infinity is approximation of the target distribution, right? But is this approximation optimal in some sense? Is this the one which would minimize the KL divergence with respect to the target distribution or other things? That's
a very good question. So first of all, I will answer your question in a moment. Just to comment on this equation. So this mu infinity here is the steady state of the evolution of this model, right? So we hope that this mu infinity approximates e to the minus f in the end. And what you see from this formula is that it is Gaussian. So this method actually always gives you a Gaussian steady state. And this is the steady state equation, no matter what alpha. So no matter whether you're discrete time or continuous time. And even to solve this mu infinity explicitly, in the case where your target is not Gaussian, is actually very difficult. So if you're in the Gaussian setting, then this is explicit, and that's what I showed you earlier. But yeah, so this is not straightforward to solve in the non-Gaussian setting. Now, how close is it? So what this actually gives you is so as beta, so this mu infinity depends on beta, right? And what we show, and that will come in a few slides, that as beta goes to infinity, then this mu infinity will converge to the Laplace approximation of your target distribution of the e to the minus f. Now, is it the closest one? I mean, we know that in KL divergence, the closest Gaussian that approximates some probability measure is the Gaussian that has the mean and the covariance of that probability measure, right? And so here we're approximating e to the minus f with the mean and the covariance at that point theta star, which is the minimum of the f. That's what the Laplace approximation is doing. Yeah, I think that's the best answer I can give you at this point. But there might still be some sort of questions to be clarified here, actually. Okay, so now this is in the non-Gaussian setting. I kind of didn't put all the assumptions here explicitly, but I will give more details on the assumptions later on. But just to say that here, the only results that we were able to prove on both the mean and the covariance for the non-Gaussian setting is in one dimension and under the assumption that the Hessian of your target is uniformly bounded above and below. So this is a general assumption that you've probably seen in many sampling algorithms, it is more general than Gaussian, but it's not the most general thing that you might hope for. Now, the reason why we only get convergence rates in one dimension and not in any dimension is purely technical. There is no sort of methodological obstruction. So what we need in order to get these estimates in beta is we need to actually work out exactly the rates in beta, the higher order terms in the Laplace approximation. And if you're in more than one dimension, that just becomes incredibly tedious. So it's just kind of a question of manpower and time rather than really the possibility of going higher dimensional. Yeah, so first of all, so we know that this method converges to a Gaussian with mean and covariance depending on beta. And so this theta star here is the minimum of f that we want. And the C star is the inverse of the Hessian of the target evaluated at this theta star. And we have the rate of convergence 1 over beta here. And then, I mean, all these, this convergence rate, we got it for initial Gaussian, because since we know that we're, where we're going is a Gaussian, and we know that the method preserves Gaussians, we might as well start as at a Gaussian, make our lives easier. And then you just argue on the moments. Yes?
What is K?
K is a constant which depends on the, it's a constant which depends on the condition number of your initial covariance that you start with.
Okay.
Yeah. And also on your target. Yeah, it's kind of this K is kind of a comparison between where you start and where you're going in terms of the covariance. Yeah.
So if your solution is actually a Laplace, then you don't need sampling, right? Then you can just use optimization to get to the maximum posteriori and then do expansion around it, quadratic expansion. And
yes, so you're saying that if my target is Gaussian, I don't actually need all of this. That's yes, I agree with you.
Even if it's not Gaussian, you can do Laplace approximation around the peak.
I mean, if you have a target that is Gaussian, there's many things you can do, right? I mean, there's many very nice.
Even if it's not the Gaussian, right?
Okay.
You're saying your solution is Laplace approximation around theta star, which is the peak, which is probably maximum posteriori. You can get to that without sampling, right? You can just do optimization and then expand around it and get, find a difference, Hessian, or something like that. Let's find a difference. You just define a difference in all directions when you get a Hessian. You build a Hessian difference.
I'm not exactly sure I understand. Oh, yeah, let's talk afterwards about it. Okay, so another comment maybe that I've just talked about something now, but you can also use this for optimization. And the only thing you have to do is basically not blow up the covariance along the flow to make sure that particles collapse to a point. And then that point will actually be the theta star that you're looking for. And so here we just have the 1 minus alpha squared instead of another 1 plus beta. And I have to say that these rates are not optimal. They give you convergence in Wasserstein, but I'm pretty sure that we can do better than this rate. And this P is just something that comes out of the calculation, but we're not able to bootstrap on it in the same way that we were able to do for the sampling case. So I think there's still room of improvement for these convergence rates here. Okay, now this is going to be interesting if I can show you some numerics. Yes?
So you said, so with this choice, you obtain an optimization method. Why? Why?
Because in that case, you can check that the steady state of the model is actually a Gaussian of covariance 0. I mean, it's just a Dirac. And the Dirac sits exactly at the theta,
okay, thanks.
or converges to the theta star. I mean, this is very similar to what I showed you on the CBO method. I mean, it's basically this argument. Okay, so let's see if I can show you some numerics. Oh, before I do that, okay. So I should say, all the numerics that I show you have been done by Urban Weiss, and we have a Figshare online where you can look at all sorts of different versions of also other applications. So I just picked like one very simple one that I want to show you here, but I encourage you to have a look there in case you want to know more. So this has become a kind of benchmark toy problem for solving inverse problems. So just a 1D elliptic boundary value problem where you have an unknown diffusion coefficient and an unknown boundary condition. And given θ1 and θ2, you can actually solve this explicitly. So this is very nice, right? So you can write down this solution P, and now this becomes your forward map G is just a function of these theta's, just fix 2 points where you collect data and you corrupt them a little bit with noise. And then you can plot how your target function F looks like, and then test your method on it. So let me see if I have the simulations for that. Something. I might not actually have this one here. Okay. Well, let me show you the optimization one instead. Sorry. So what you see here is that basically, I should have put the image where you have. I put the wrong image here. So basically, the samples collapse very quickly to the region where you see most of the mass, and then you can compare that to several other methods that have came out recently, and compare the rate of convergence there. Okay, so some of the sort of typical functions that are very difficult for optimization methods are these functions that have a lot of local minimizers. And these consensus-based techniques are very good, specifically at overcoming that challenge. And so 2 choices are this Ackley function and Rastrigen function. You don't actually need to know look at the whole formula of this. I mean, just look at the pictures here. The global minimum is where this crosses. And then you see that it has a lot of local minima, kind of like an eggshell. And so let me just show you some simulations for that, since I have them here. You see that the red cross is the weighted mean. Play that again. And something that you may also notice is that we're actually changing the beta along the evolution. So, you know, the kind of analysis that I showed you is for fixed beta. But if you play around with this, you actually see that you would like your beta to be large. And so if you increase the beta along your evolution, then that really helps. And so here, what we did is use the effective sample size as a guidance for how to choose how to fix the beta. But there's no analysis that we have done on this. So there's kind of a very interesting question here. You know, why is this the good choice? Is there maybe a better choice? Like, what would be a good choice for an adaptive beta for this method? And then just maybe show you one other one. Yeah, so you see that particles get stuck a little bit in the local minima, but then they get out and they find the global position. Okay, so now let me show you sort of an overview, because this has been probably a lot of different equations. So just to summarize, so here this K0 is sort of the comparison between your initial covariance and the target covariance. So here, this is now the Gaussian case. So I will sort of give you the summary of the Gaussian case and then the summary of the beyond Gaussian case setting. And so all of these rates that we obtained for the sampling and the optimization case, they're sharp in the sense that we have upper and lower bounds for them. And yeah, as I already mentioned, you see that choosing alpha equal to 0 is actually the best choice for the discrete setting here. Okay, and the same also for the optimization. And so just as a summary, we get algebraic convergence for optimization and exponential convergence for sampling. And those rates in sampling are also, I mean, in the Gaussian case, analogous to what is known for ensemble common methods like ensemble common inversion and ensemble common sampling. We have sharp convergence rates, and yeah, smaller alpha is better. yeah, I also mentioned that, yeah, larger beta is better. Now let me mention something about the steady states. So actually any Dirac measure is also steady state. And so, you know, what you, in addition to the Gaussian that you're actually looking for. And so if you would start at the Dirac, then you wouldn't move. But what you can show is that if you start at something that is not a Dirac, right, then you converge not to a Dirac, but to the targets that you're actually interested in. Now, beyond the Gaussian case. So this is the assumption that we're working with. And for the results that we have in one dimension, we have actually an additional assumption that the f cannot grow more than e to the x squared. And its derivatives as well. And so you see again that we get algebraic rates for optimization and then exponential rates for the sampling. And this is where this n to the minus p and t to the minus p come in, and these are definitely not optimal. So here we're not yet fully satisfied with what we were able to obtain on the rates. But apart from that, I think this is one of the sort of strong points of this method, that you can actually prove something about the rates of convergence beyond just the Gaussian setting. Okay, so some comments on steady states. So what this method gives you is basically a steady state whose mean is close to the minimizer of f. And for large beta, it converges to, for beta going to infinity, it converges to the minimizer of f. And this is actually true in any dimension. And here we have 1 over beta rates we got in any dimension. Now the other statements are just in one dimension. So we get a steady state that is arbitrarily close to the Laplace approximation of the targets. This is what this method is giving you for beta sufficiently large, of course. And then I already mentioned this mu infinity is a steady state for all the different parameter choices that you might want to make. Okay. And so just as a takeaway, yeah, so the Laplace approximation, the key principle is sort of that you reweight any measure by e to the minus beta f, and then this approximates the Dirac sitting at the minimum. Yeah, so if you rescale your covariance with the right factor, then this allows you to recover an approximation of the target e to the minus f. And then if you don't want to sample but to optimize, you leave out the factor 1 plus beta. Okay, and we're able to get rates beyond the Gaussian setting. So yeah, this is just an overview. As I said, like, because we have this interacting particle system, I mean, this is true for all these methods that use interacting particle systems. They're nicely parallelizable if this forward map is very expensive to evaluate, and we do all the analysis in the mean field perspective. All of this is derivative free, so this is very useful for these very expensive inverse problems. We have exponential convergence for sampling, and this method is also affine invariant, which basically means that if you apply an affine transformation to the input data, so the measure where you start and also your target, and then you run the model, is the same as if you run the model and then you push forward with the same affine transformation. And so what that allows you to do in some way is, yeah, that's one way of thinking about why you get convergence rates that are independent of the target in the Gaussian setting, because that allows you to kind of rescale the covariance to be identity by applying such an affine transformation. And there's a very nice work on this by Alfredo Gamuno-Inigo, Nicolas Nüsken, and Sebastian Reich, which I cited here. So if you'd like to know more about these properties, then I encourage you to look there. And there's many open questions actually in this general area, of course, but I just listed like a couple here for this specific problem. Yeah, one is the question of adaptive beta, if we can say anything about that. then proving convergence on the particle level and also the approximations between the particle level and the mean fields equations. And then if you can do anything about the sampling error. So, one also recent paper that came out, calibrate, emulate, sample, I think is a very nice idea where you say, well, I have some sampling method like this one that gives you some approximate samples of your target. And now you can take these approximate samples to create a surrogate model for your forward map G, and then use a Gaussian process emulator to sample more cheaply from your surrogate targets. And so you can think of this method kind of plugging in as the first step in here. Okay, so this is all that I wanted to say. And yeah, thank you very much.
Yeah, thank you very much for the very nice talk. I've got a question. Does this method possess the subspace property, meaning that the ensemble does not leave the initial subspace?
Yes,
it
exactly.
Does.
Yes, exactly. Thanks to this fine invariance. Yes.
Okay, so your underlying assumption was then that the initial covariance is invertible or something like that, such that you can actually get the Hessian of the function f in the end.
That the initial
ensemble, that the covariance of that ensemble is invertible. So basically that you already cover the whole space. That was an underlying assumption.
Yes,
okay.
yes, that's right. Yes, and it makes up, like you would like to start with something that's actually quite spread enough in the space so that your particles explore enough initially. Yeah, that's very important. And that also turns up in the rates actually in this K0 and the K, because that's exactly comparing the initial covariance to the target covariance explicitly in the Gaussian case. And that's exactly where that shows up.
Okay, thank you.
Yeah.
Any other questions?
Yeah, thank you for the talk. So I actually have two questions. So then there's a naive one. Do you use how do you use particles to compute things like M of beta and C of beta? Do you use some kind of like crowd density estimators or these kind of approximations, or is there any direct way to do that?
I actually have a slide I put in the appendix on this. So there we go. So you basically just work with the empirical measures on the particles. So like the mean field equations that I showed you, you can just approximate the integrals by sums. And then you have, so these are coupled equations for the particles, and the coupling happens exactly through the means, right?
Thank you. So another question is, if you have a very highly non-convex potential, how do you fix that? Because you're always remain a Gaussian. Do you have any idea to?
What do you mean?
If your target is highly non-convex, then but your dynamics preserve a Gaussian. So do you have any ideas on how to fix that difference using the landscape of the potential?
No, that's a very good question. I mean, what this method is going to give you is only Gaussian approximations all the time. So of course, if your target is not as Gaussian, is very non-Gaussian, then those approximations might not be very good. So that was exactly this question of, can you do better by somehow correcting the samples? Well, that's a very important question.
So you motivated this in the beginning by saying this is for expensive functions. And for optimization, in case of expensive functions, the usual tests are, well, you have to minimize the number of calls. And I know that for 2D actually and restricting, they usually need a few dozen calls, right? Let's say 30 or so. Do you think your method can be competitive in that, in finding, for example, the peak with just a few dozen calls?
I'm not sure on the exact numbers in that case, but
the plot you've shown is hundreds of articles and and several steps, right? So that was more like thousands.
So what I can tell you is that this method actually gives you very good approximations with comparably a lot less particles than what you would need, for example, in MCMC methods. Also, if your forward map is if your F is very expensive to evaluate, then of course you would like your number of particles to be very small, because that tells you how many times you have computed the F for the means and the covariance. But all the analysis we did is in the mean field setting, right? So now on the one hand, you want to take few particles because of the more, if your F is very expensive to evaluate. On the other hand, everything I just told you is for the mean field equations. So there's clearly a gap, right? And so I think there's some important follow-on work that should happen, looking at exactly those questions for the Fokker-Planck equation that is satisfied by the empirical distribution of the particles, right? So yeah. Maybe just as a follow-up on this, I'm very happy to report also that this just got accepted this week. So, this is very fresh. So I think there's actually, I mean, this is some very important question there to answer. And I think there's a couple of other questions, and I hope there will be follow-on work going in that direction.
So I think global optimization is just a very difficult problem by itself. So just for the convex setting, empirically clear, the last example is entirely highly non-convex. So they were able to converge, so which means there is a potential. It's just the analysis probably hasn't got. Am I understanding it correctly?
Yes, yes. I mean, there's with this method as well as far as I understand, many other sampling methods, there's often a very big gap between what you observe works and then what you're able to prove about the behavior, right? So we were kind of very happy to even just go beyond Gaussians as long as you have uniform upper and lower bounds on the Hessian. Whereas in practice, it seems like this is actually doing very well. And compared to the ensemble common sampler, for example, also doing very well. So yeah, I think if there's anything that we could say for more complicated problems that actually appear in applications, I think that would be a huge step forwards.
I think particle level of proof will be definitely the way to go, because that really tells you if you converge to the global minimum or not.
Any mentions? Or I have a quick question. So I just wonder that because you advertise this method as a gradient free, so if it's not hard to compute the gradient, how does this method compare with a gradient-based method?
I would assume that gradient-based methods would do better.
Okay.
In that case.
In high dimensions, low dimensions not the same.
Yeah, that's right. Yeah, that's right.
All right. Okay. Thanks, Franca, again. Oh, yeah.
Yes, thanks for the talk. So I was trying to summarize what you get in the case of optimization. So you have the method is a derivative free, and you have so convergence to the. So you said the steady state is a Dirac, right? Dirac at the minimizer of F, right? And
well, no, you have a target. Well, you have a Dirac as a target, and that sits at some point that depends on beta. And as beta goes to infinity, then that point converges to the minimizer of F.
All right.
Yeah.
Okay. And the rate that you showed in the last slide before going to the numerical section.
This one?
No, before. No, after that, I think. The last slide before the numerical.
So this one.
Yes.
These rates.
Yes. So what does it mean?
So as I said, I don't think these rates are optimal.
Yes, but I just want to understand. Right. Convexity. So it does. Okay.
And I'm happy also to chat in more detail and show you how exactly that computation goes for this. Okay, and also why we get stuck here, right? If anyone can tell me how we can bootstrap these estimates, I would be very happy.
Yeah. Okay. Okay. Right. Thanks. Thanks.
So let's move on to the next talk. Thanks.